What's up, everybody? Welcome to lecture 5. It is over section 3.4. You'll notice I kind of rearranged things a little bit. I just thought 3.4 made more sense to be taught here because it leads into section 1.7 fairly well. And it just kind of picks up in a good spot compared to the last lecture, I think. So for that reason, I'm going to go ahead and present it here. What section 3.4 is all about is this idea of horizontal asymptotes in limits as you let x tend to plus or minus infinity. So to either extremes of the x-axis, right? And what we say is that if the limit as x approaches infinity of f of x is equal to L, or if as the limit goes to negative infinity, our function approaches k, then we would say that the line y equal to L or the line y equal to k is a horizontal asymptote. And I've got a couple of examples here just to demonstrate a little bit of what this all means. So in this case, we've got this function that as we go off to infinity, it gets as close as you want it to this line y equal to L. It would say that the limit as x approaches infinity of this particular function is equal to L. So y equal to L here represents a horizontal asymptote. Similarly, in this case, g of x, you notice will oscillate up and down, up and down, up and down all around that line y equal to n. But we approach it. As we go on forever, we just kind of decay into it, right? Kind of like the car shocks. It bounces up and down, up and down, up and down until it hits that little spot. That is what this function's doing, except it's doing it around the line y equal to n. And we would say here that the limit as x approaches infinity of this function g of x is equal to n. Now, on the other hand, let's consider the case where we're going to negative infinity. Here, this thing does this really weird loop thing, but as you approach negative infinity, it decays into this line y equal to n. So we would say that this function h of x approaches n as x approaches negative infinity. So this is just kind of an intuitive description of all of this. In just a second, I'm going to go and set up another problem and show y'all how this is actually done, how it all works out. Cool, let's do that. So before we get into this first example here, I wanted to give y'all another kind of brief example of a function that has two different horizontal asymptotes. You'll notice previously I said nothing about it being limited to having a certain number of asymptotes, right? A function could have two different asymptotes, one going towards infinity and a different one going to negative infinity. That is totally possible and totally okay. And it doesn't have to be the case that they're in a particular order, right? Take the negative of this and you flip it. So just something to be aware of. But what we've got here in this graph is the function arctangent of x. So we've got j of x, some random function, is equal to arctan of x. And as we go to infinity, this arctangent function is equal to pi over 2. You got a horizontal asymptote, right? At pi over 2. And as we approach negative infinity, this arctangent function, well, it's going to go to negative pi over 2. Having said that, we will be talking about trig functions in this class. So, if you're uncomfortable with trig for whatever reason, I would strongly encourage you to check out the lecture notes that I left as review on Blackboard. you'll notice I've left my entire lectures for trig up there for y'all to check out. Similarly, I've done the same thing for algebra. So if there's anything in algebra that you're a little rusty on, maybe synthetic division, I would strongly suggest you to go check that stuff out. Some things that I've noticed in the past that might trip y'all up a little bit would be things like domain and range, synthetic division, things of that sort. Every now and then, different trig identities. Certainly understand why anyone would forget trig identities. It's totally understandable. But if you had, do go back and check out those notes. They will help you, and that is what they are there for. But saying that, having said all that, let's check out this example here. In this example, we want to find the limit as x approaches infinity of the arctan of x minus pi over 2. Well, to do that, we can take advantage of those operation with limits we were talking about in the second lecture, I believe it was, section 1.5. What we can do is we can break this up using the sum and difference rule, right? This thing is equal to the limit as x approaches infinity of arctan of x minus the limit as x approaches infinity of pi over 2. But hey, pi over 2 is a constant, so that limit is just going to stay the same, right? It's not going to change. It's just going to be that constant value, pi over 2. And based on what we were just saying a second ago about arctangent, well, as x approaches infinity, arctangent approaches pi over 2. So this is going to give us pi over 2 minus pi over 2, or just 0. Now, having said that, there's another way we could have seen this. Another thing that you may want to review from algebra. By knowing the graph of this, and just knowing the general behavior of everything, we can see here that we're shifting arctangent down by pi over 2. Well, if we shift it down by pi over 2, that means that horizontal asymptote is going to be shifted down by pi over 2. Well, pi over 2 minus pi over 2 is just 0. So just knowing the way graphs translate in graph transformations as you change functions, knowing how all that behaves is going to be of some help in this class as well. So that's something else that if you're rusty on, do check those notes out and feel free to hit me up whenever you need. Having said that, we're going to look at one more example because there's a nice little algebra trick for that problem that we're going to use in this class a good bit. So let's go check that out. All right, so for this next example, we want to find the limit as x approaches infinity of 3x squared minus x minus 2, that quantity divided by the quantity 5x squared plus 4x plus 1. Okay. Well, both of those are polynomials. The denominator doesn't go to 0. So couldn't we just apply that limit directly to get infinity over infinity? Seems logical, right? Unfortunately, no. Infinity over infinity is what's called an indeterminate form. And when you see it, it means there's some more massaging in the algebra that needs to be done before you can actually solve the problem. Okay, so if that's not the answer, what are we going to do here? take a couple seconds to think about this. What might we do that doesn't functionally change anything? It doesn't actually like do anything. It could help us solve this. Couldn't we, and this is just a thought, couldn't we multiply by 1 over x squared divided by 1 over x squared? Can we do that? Why would we do that? Well, it gets rid of those x squares. It does some other things throughout these two polynomials, right? Let's check that out. If we do that, that's going to give us the limit as x approaches infinity of, well, 3x squared divided by x squared, that's just 3, minus x divided by x squared is just 1 over x, minus 2 divided by x squared is just 2 over x squared, all divided by 5x squared divided by x squared, well that's just 5, plus 4x divided by x squared, well that's just 4 over x, and 1 divided by x squared is just 1 over x squared. Huh. Well now look at what happens here. This goes to 0, this goes to 0, that goes to 0, and that goes to 0. So all we're left with is 3 over 5. And that is the limit of this rational function. And it's tricks like this that we should be aware of. Multiplying by 1 is one of math's favorite tricks. Like, mathematics survives off of this idea of multiplying by 1. You use it in almost everything. So something to be aware of, you can do something like this, right? Because multiplying by this value, effectively just 1, isn't it? 1 divided by x squared divided by 1 divided by x squared, yeah, that's just 1. That's x squared over x squared, 1. Using tricks like this will help a lot, and that's why I wanted to show this particular example. And so let y'all know that these are okay tricks to use. Sometimes we will add a 0 in. So maybe you have some function f of x, and you want to add a constant, and then subtract that constant. And that'll let you rearrange things. We're actually going to see that when we get to derivatives. One of the proofs for the derivatives, for a particular derivative, we'll use that trick. So again, these sorts of things, adding a 0, multiplying by 1, totally okay. Use them. Absolutely use them. But having said that, let's keep going. Okay, so now we're going to get into the weeds here. I'm not going to lie, this is going to be weird at first. It's calculus. That should be expected. What we're going to be talking about from this point on, well, I shouldn't say from this point on, for the rest of this lecture, this last little bit here, and the next lecture, is the precise definitions of the limits. So what exactly these things are trying to tell us. To start off with, thought we'd look at the precise definition of a limit at infinity, because I think this is the easier one to grasp first. So what it tells us is that if this is true, in order for this to happen, for the limit as x approaches infinity of f of x to be equal to L, if that's going to be true, then for every epsilon greater than 0, there's an n such that if x is greater than that n, the absolute value of your function evaluated at some x greater than that n minus L is going to be less than epsilon. What? That's, what is this, right? That's the question. I think this is the most easily understood by looking at it through a picture. What we're saying is, this function, in purple here, the oscillating function, it has a limit as x approaches infinity. We say that limit is out. Well, in order for that to be true, then there's got to be some x value or some n value such that for every x greater than n, you can squeeze the difference between x and L, or f of x and L, within some epsilon thing. Okay, right? Well, let's look at the picture. We get this function, like I said, the limit goes to L as x goes to infinity. So we're going to pick some x value, or some n value. This n here. Our function is here, right? We're going to say that the difference between our function and L for every x value to the right of this n will be less than this distance here, this current distance. Okay, let's look at that. Let's see if that's true. In order for this function to decay into infinity, we're bounding it from above and below for every x greater than n. So we're picking this in. We're saying, for each of these n values, or for each of these x values greater than n, we can sort of bound, put a box around, in some sense, our function. That box above and below L has a height of epsilon. Okay. Well, picking this in, the distance between f of x at this n value and our height of our function, or in L, we call this epsilon. And then we're going to go epsilon above L. We're going to say, all right, we claim that this function is going to be bounded between L plus epsilon and L minus epsilon. So the bottom there is bracket. That's what we're doing over here, right? Well, we look to every x value to the right of n, I'll be damned. The thing is in between those two lines. Every value of your function oscillates between those. In fact, if you were going to pick another value, let's say instead of n this time, we're going to pick m. And let's say m is, we've almost done green chalk. Oh, you know what? I've got my box here. I'm going to grab my green chalk from the box. Let's now choose another value. Let's call it m. If we wanted to, we could say the distance between our functions at m here and L, it's another epsilon. And if you were to look at every value of x greater than n, again, your function is bounded above and below by a distance of epsilon from L. And that's what this thing is doing. It's saying, go further. Pick a new value. All right, call that value whatever you want. So start at n, go to m. Can you do this same thing again? Yeah? Do it again. Yeah? All right, well when you keep shrinking in, right? So, choosing in, then choosing n, if we wanted to, we could keep going, right? And every time we did, that epsilon band would have to shrink. It would shrink, and it would shrink, and it would shrink, and it would shrink, until it eventually got to L. And that's what these precise definitions are going to be doing for us. They basically squeeze your solution, if the limit exists, into a particular spot. We'll see later what it'll look like if the limit doesn't exist. That said, I should note here that the limit at negative infinity is almost the exact same, except it's for x less than n. Because then it would be moving in the opposite direction, right? So having said that, I'm going to end the lecture here. Like I said, next lecture is going to be all about 1.7 in these precise definitions of limits. We're going to look at one or two examples with those precise definitions. Generally, these are the hardest things, I think, in calculus point blank. You'll hear me say something similar to that all semester. This is one of the hardest things. This is one of the hardest things. This, I think, is actually the hardest thing. So having said that, if you get past this video, the words are behind you. So something to cheer about, right? But anyhow, I'll let y'all go. Have a good rest of your day and see y'all in the next lecture.